Okay. All right. So, welcome to the latest Trees Around the Globe Student Research Campaign webinar, and welcome to year 8 for the campaign. Today, this is a State of Trees, October 2025. Welcome to year 8 of the Trees Around the Globe Student Research Campaign. That's a bit redundant, but today is the 21st of October, 2025. And like I said, welcome to year 8. This is a shareable that you may have seen on our campaign website. This is on the landing page. And these quotes here that we have were quotes that were part of our final campaign, which was a campaign webinar, which was last month for year 7. And these were ones that were put into our chat or, that were captured in the chat log for Zoom. So we included those in the shareable that is put up on the website. And even though the year 8 began on the 1st of October of this year, this is the first webinar for the campaign for year 8. So we're super excited to have you here. And a lot of people who are normally here for our campaign webinars sent me some emails. I got about 15 or 16 emails since Friday from people who said they cannot be here today, and they're excited about the recording from today's webinar. So we might have a small group today, but Peter Falcon, please continue to let people into the room. That would be great. So so we're excited here to start off year 8 of the campaign. All right, so today, as we normally do, we are going to do the introduction, introduction, agenda, housekeeping, and some metrics, and then we're going to go into, Peter is going to talk a little bit about just a couple minutes, how monitoring our environment prepares us for navigating uncertainty and how that brings forth resiliency. That's just something, we've been talking, not in those not in those exact words, but that's kind of what we've been doing for the whole, duration of the campaign since we started in 2018. How we're looking at the measurements, how we're setting students up for, submitting IVSS projects with getting them to look at, these questions that they're trying to answer, these uncertain questions that they're trying to answer by looking at the data, whether it's their data that they're collecting or other globe data, or looking at the NASA data, and they're monitoring their own local environment. They're seeing how the satellites are monitoring the global environment. But we're always, no matter if you're looking at the local environment or the global environment, you are navigating that uncertainty in order to get answers, right? So with that, after that brief discussion, I'm going to take you to, those missions that we've been looking at with this campaign, that have been part of this campaign for the last 7 years. And I have brief videos, ones that, that have been created by the missions, whether they be, when we just before launching these missions, to ones that have been created, to ones that have been created just, post launch of these missions. And we're going to, start off, way back, over 10 years ago with the Global Precipitation Measurement Mission, and run through soil moisture active passive, and then through ICESat-2, the Ice Cloud and Land Elevation Satellite 2, then to the Global Ecosystems Dynamics Investigation, or GEDI, and then to Landsat, and then to NISAR, which you've heard a lot about. Last month's webinar, you heard from Dr. Erica Podest, and you heard from her also back in November of 2024 about the NISAR mission. And NISAR mission at NASA is, with Earth science, it's the kind of NASA Earth science is bread and butter right now. It's one of those one-stop shop Earth observing satellites right now for NASA. Kind of does it all. So it's one of those things that we really want to highlight with this campaign. And then you heard from our speaker 2 months ago about the GRACE missions. We have the GRACE mission, we have the GRACE follow-on, and then we have, launching in several years, the GRACE continuity mission. So I'm gonna showcase a video for each one of these missions to kind of refresh your memory, and the people who are going to watch the recording of this, refresh your memory about what these missions are, and then to bring back how they're important to what we're looking at with this campaign, whether it's trees or land cover or greenings or carbon cycle, and looking at that change over time bit that we've been talking about so much. And then after that, I'm going to turn it over to our own Peder Nelson, and he's going to bring it all together. The idea of monitoring our environment from space, navigating that uncertainty, and how this all can be brought down to that local level. And then following that, right at the end, we're gonna, have a little discussion, a little powwow about, what, upcoming, potential campaign fall IOP for tree height and land cover. And what I will say too is, we're running this campaign webinar, and we do understand, right now in the United States, we have a government shutdown. Okay, so you may have noticed on the Globe website that there's a disclaimer at the top. It says we are not updating this website during a government shutdown, because the website is a .gov website and it falls under the US government. So you'll see that on all the NASA websites and also on the social media pages that, when there's a lapse in funding, we're unable to, update these websites. So with this campaign, if you go to the campaign page and you go to the webinar page, you will not see any updating until the government shutdown is over and the funding is restored to do all this stuff. So I just wanted to give you that heads up. That's just the way it works on our end. So, but you will get this recording, first thing tomorrow, because I will put it up on YouTube for this webinar, and I will send you the direct YouTube link. It's just you will not see it on the webinar page for our campaign until we're able to, till we're allowed to get it back up there after the government shutdown is lifted. And we don't have any idea when that's going to be. Okay. So just want to give you that heads up. All right. So, excuse me, battling some issues right now with my voice and stuff right now. I apologize for that. So as you know, we have this gray map here. We have our participants from 70 countries are part of the Trees Around the Globe Student Research Campaign. So I had to create, I had to make the font a little smaller because now we're in year 8. So I draw your attention down to year 8. Here we have, we had a big jump in numbers. I reported on this at one of our internal meetings a couple weeks ago, but we actually have a pretty big jump. And, we actually have something going on right now with Globe. We have the Africa IOP, which is in support of Northern Arizona University and the NASA GEDI mission. So that is one that has been going on for a couple months, and it ends at the end of this month. So there's a lot of tree height measurements coming in, as you know, and you'll hear more about GEDI, of course, later. But if you've been part of this campaign for a while, you know that GEDI is, an instrument on the International Space Station that measures tree height kind of around the mid latitude, 56.1 degrees north to 56.1 degrees south. So, a lot of tree height observations have come in to support that mission, that IOP, the Globe Africa IOP. So you can see here we have over 1,700 tree height measurements just since October 1st from over 570 global sites, and we just topped 1,000 land cover measurements from over 370 global sites, and over 560 green up, green down measurements from 96 global sites. And I looked, and just about every one of those comes from the European folks with the European Phenology Campaign and the fall observation. So autumn observation. So thank you for that. So then, as a whole, we are at this is webinar 86 for the campaign. We've also had 34 special webinars, so we have a total of 120 campaign webinars. We have, as part of the campaign, 82 blogs. We just topped 370,000 views. And then draw your attention to the bottom here. These are our full campaign metrics for the data coming in for the measurements, and we have over 253,000 observations from over 77,000 global sites, and this is for the life of the campaign. And always my disclaimer is that we know that all these observations are not coming from only the campaign members, but we do use this because this is for the life of the campaign, and this is great for the students to use if they want to use some type of, some date to start with. Data. Don't remember that, we started this campaign at the exact same time the ICESat-2 satellite. As you know, we like to do quotes, and so since we have Peter talking today, doing a part of the feature presentation today, we have a quote from Peder Nelson, and navigating uncertainty is a that leads to a little teaser right there. I know you're talking a little bit.
Oh, hey, Brian. I really, appreciate right now the sort of scientific focus that we have on sort of how good are we doing with our predictions, and those predictions can be around a lot of different things. But one thing I want to sort of highlight today is uncertainty can be quantified, and it should be quantified, and it should be used to help guide us where we actually go on the ground. And one of these things that is important, because I like to see like the things behind me, which are the pretty numbers, and those tend to be the mean or the averages, right? So that we can understand and describe to each other how confident we are in what we're using for our decision making. So, just recognize that there are certain landscapes in the world that just have more uncertainty. And that's actually one big thing that we have revealed every time we do a science experiment. We get indications about where to focus next. And that is actually exactly why we're having this intensive observation period with Northern Arizona University. Is over the last 5 years, they have not only seen uncertainty in their measurements, but we as the globe community have also helped to reveal places that need to have a little bit more of a focus. And so, this idea of uncertainty can sound like a bad thing sometimes, but it's actually part of our life, right? And how we work with uncertainty is something that is a science piece, but it also helps guide into actually our day-to-day lives. So I hope that when we're talking about this idea of uncertainty, there's a lot of things that come with it, and so as a teacher, I really like this idea of uncertainty versus certainty, because rarely are we always 100% certain about something. Usually there's a little bit of doubt. There's a little bit of maybe measurement error that leads into, results being a little bit different than what we expect. And so, as we go into this 8th year of our campaign, part of what I want to highlight is that the Globe database is one place where you can get information about the world. And if you only focus on that, it will lead you to places that may not fully quantify or fully describe that location. This is the uncertainty that we're talking about. And this is what led me to the Globe program, actually. And I want everyone to kind of think about, other programs that might be out there that might be collecting very similar data. And part of the job of a scientist or of a community is to try to bring together all of those things that describe a place. And that's what we as scientists do right off the bat, is try to find what are the satellite measurements that can complement what we're seeing on the ground. So embrace the idea of uncertainty, because it really does open up the space for research going forward. So if you focus on these places where people are having a hard time, like we're going to highlight today, how you find those uncertainties in your locations, in your community, is really a place where we can all work together, as a community, and as a global community, to hopefully have a better understanding of these trajectories that we're on together. So Brian, with that, let's go into some of these definitions, because Yeah, I think it's
Yeah.
really important to recognize that part of uncertainty comes from a lack of definitions and a lack of understanding of what each other is actually talking about. So, Brian, dive into what we mean here by uncertainty in this case.
All right, I will go through these definitions, and then I'm going to pass it over to Peter for a couple words. But yeah, so I threw this together just for I know some of our our international audience for this, but uncertainty and resilience. So uncertainty can be defined as a situation in which something is not known or something that is not known or certain. It refers to situations involving imperfect or unknown information. It applies to predictions of future events, to physical measurements that are already made, or to the unknown, and is particularly relevant for decision making. And then resilience, the ability to maintain capability in adversity, operate under stress, and recover to an effective posture and adapt to changing conditions. It can refer to bouncing back from adversity, not avoiding it, and it involves a combination of behaviors, thoughts, and actions that can be learned and developed. The term can also be applied to systems, organizations, and materials, referring to their capacity to withstand and recover from disruptions. So, with that said, let me pass it over to Peter to say a few things. So, Peter, would you like me to unshare?
No, it's fine. I did not put the slides together, actually. I just
Cool.
was going to say a few words. Actually, there's not much more I can add. I think Peter hit the nail right on the head, which is saying we have here. He described perfectly what we're going to discuss today. I would say in our last, planning meeting, Brian and Peter and myself, as we talked about the past 7 years, going into 8 years of doing tree webinars, we talked about what everyone else is I imagine talking about or is curious about. What's next? What's on the horizon for the GLOBE program? What's going to happen to the trees webinars? Where do we go from here? And with all that, you're picking up on some terms here, some key terms: uncertainty and resilience. With all that uncertainty, with our climate, with funding, even with our political systems, not just in the U.S., all over the world, we talked about, what do we do next? And throughout all that uncertainty, we thought the one thing that we need to make sure we do, and the one thing we need to maintain and encourage everyone on the Trees webinar and the GLOBE and scientists around the world, is to maintain their resilience, is to continue doing what they're doing, making sure that they continue making these measurements. Because to be quite honest, the measurements we do today, the data that we're collecting, is not only being used to make the most accurate measurements and models, to study our planet, but also the data that we collect today, it's going to far outlive our lifespan. I mean, other researchers who probably aren't even born yet will be using that data to build even better models, to understand what's going on with our planet, to make even more accurate models. So once again, we just wanted to encourage everyone, from our partners to our teachers to our students, to maintain that resilience, continue with those observations, with those environmental measurements, because they are extremely important and they will far outlive, probably this program, these webinars, our lifespan. So once again, in these uncertain terms, uncertainty, what's going on with our planet, the one thing that is certain is that the resilience that we have today and that we show tomorrow will live past the problems that we're going through today. So I didn't put together any slides or anything. I just thought something that we we discussed. I imagine everyone else on this webinar and those that couldn't make it today, these thoughts have crossed their mind, as well as what's next. So we don't know what's next. We don't know, future of the program. But once again, we do know that we just have to maintain that resilience in everything that we do, including, and most importantly, in the science that we do. So just wanted to end with that and say, encourage you to continue doing what you're doing, stay the course, stay strong, and continue teaching and passing on that knowledge to the next generation of these future scientists. Thanks, Brian.
Excellent. Thank you, Peter. And Peder Nelson, would you like to add anything to that?
No, I'm really excited to, think about how we actually move forward with resilience through this uncertainty, right? And I think this is one of those things where it's not just the words on this screen here. We actually have framework, processes, things that have been developed over time that actually helps us to become resilient as a community to uncertainty. And when you don't know what's going to happen, sometimes things that you've done in the past will become really, really important. Or you might find new pathways that you have to forge, right? So I think one, getting these words down is really important, but it follows up with actions, and we see actions by looking back in time. And this is one of these fun things that I really appreciate about satellite data, actually, is it helps me put together understanding of the world when I wasn't paying attention or wasn't thinking about that larger force that was influencing me. Because this overview effect that Brian is taking us into right here, I think, is really, really, really important as we think about what it means to be resilient, right? And what it means to have uncertainty. And how precise do we need to be with our numbers to actually understand this world around us? And I think that's, some of the important things that I've learned over this campaign and during this time with the Globe community is actually contributing to this database of knowledge that, the way it's put together reflects the people who are here at this moment in time. And this connection to what we're measuring with this sunlight, and all of these relationships that we can describe mathematically and give us some things like this, are also literally the things that we're experiencing on Earth, right? And so I really, really appreciate not only measurements that come in as a scientist, right, but this larger effort that we're on, where it all depends on the spatial scale, on the temporal scale that we want to be thinking about. And so, when we talk about uncertainty has, like I said, something that can be quantified over time like this. But this is one of these things that scientists recognize is a really important part of how we move forward. And how, again, some things do take 10 decimal points, but other things only take 1 or none. And to me, it all goes back to this reference. What are we referencing ourselves to provide us with that certainty that we're after? And so I really, go back to how precise do we need to be with some of our measurements to really understand a larger trend that's happening globally like this, but also how that feeds into our understanding of what will happen to Earth over millions or billions of years. Like I just saw a nice report coming out. And it's great to think long term, like 1 billion years. You can do it. But I think coming back to, human time, my life, what we're trying to do and what we might experience on this day-to-day part is, I think, one of these grand challenges that we have, right? To both think locally and act locally, while at the same time keeping in connection with this huge, giant process that we're just part of at this moment. So, Brian, these are the big ideas, right, that we're trying to hold together as we focus on something as long-lived, and might even long live outside of ourselves, these trees, these other organisms that are around us, right? And that to me is one of these things that these missions are snapshots in time. But our big challenge really is extending that out to maybe our whole experience, and definitely the experience of the ecosystems around us. So, Brian, give us a little sense for these ongoing data collections that I've been told are still happening, even though we might not be able to actually get at the data right now, right? That's this whole funding piece. And I'll end here with this pass off with saying, this is actually part of our resilience, right? If we can't get out there and make measurements, we've built these instruments up in space that actually allow us to maybe get to places when we can't get there. They help to resolve some of our own human uncertainty that are out there. So this is part of our resilience package, actually, is these satellites up in space that are our friends, and that can really be complementary to what we're experiencing in one location where maybe you can't get to those locations to make those important measurements. And so, Brian, how do these things really actually help us in this moment where there is a lot of uncertainty in terms of who's measuring what and where, and how does it all come together?
All right, thank you, Peter. That's a great segue. So yeah, so I'm gonna highlight some of these missions. We're gonna go all the way back to yeah, of course GPM, but it's still in space now, of course. But being this core satellite, looking at the global precipitation, in space for a very long time right now. But when we're looking at of course land cover change, and we're looking at tree height, we're definitely looking at precipitation as one of those major factors and variables involved. So even though we're not looking at specifically precipitation measurement when we're looking at when we're talking about the exact tree height and land cover measurements, and when we're doing the metrics and all that stuff for our campaign, these observations that we're getting from the GPM mission and are vital. But then we're also, when the students who are doing, our campaign related IVSS projects, they are using, the precipitation measurements and observations that are in the GLOBE database as part of their research. So, that's why it's included in here. So we're going to go all the way through here, all the way back to GPM, and we're going to, go to GPM. We're going to run through SMAP and Landsat, all the way up to the upcoming GRACE-C mission. So all of these missions here, not excluding GRACE-C, which isn't going to be launched until 2028, when we have data from GRACE, the other two GRACE missions. But we have that data. We have that data in the database. What's there? Just the the updated data. That it's not happening right now because of the government shutdown. But the data is in there right now. Past data. But these missions provide, as Peter mentioned. I don't want to repeat everything Peter said because he said it so well. But this data provides that data where one, we're not able to go, two, the data that's missing that we're not able to get, that type of stuff. And that's very common, and well known. But it also provides that data, kind of that that data that helps us support and helps us provides supporting data for the data that we're collecting on the ground, whether it be precipitation data or tree height data or soil moisture data, or land cover data. It helps us to support the data that we're collecting and comparing that data as well. On our webinar right now, we have Marilei Colon-Robles, who is the Globe Observer Clouds Science Lead, and with the clouds, the Globe Observer Cloud program, they've been doing the satellite matching for a long time, well over a million matches. So, but they've been doing this, and they've been really the groundbreakers in showing the comparisons between the data coming in from the Globe Observer with cloud observations and matching that to the satellite data of cloud observation. So that's so important, because then you get that secondary level of and sometimes even tertiary level of data comparisons to really strengthen that data set, whether it be just for observation's sake or for student and professional researchers alike, to really look at that solidified data, the validity of that data, just gets exponentially better as, you get those, increasing levels of comparisons with the data. So what I'm going to show here is I'm going to show you some brief videos for each one of these to kind of, bring back, since we're starting year 8, there's a lot. We've covered so much, just an insane amount of information over the last 7 years. So, we don't expect all the participants to remember every little thing about every mission, that we've covered. We've covered everything from satellite missions to ground-based missions to airborne missions, over the last 7 years of the campaign. So we don't expect you to remember everything. So this is kind of to bring you back to, these really, vital Earth observing satellites and instruments that really play a vital role in our campaign, because this is kind of setting the stage for that satellite based observation part of it that we're going to be really focusing on, that data part of it that we're going to be focusing on for the life of year 8 of the campaign. So let's start with GPM, and these links down at the bottom here. Once I will post those in the chat towards the end. When I pass it over to Peder Nelson after these videos are shown, I will then pop these in the chat for everyone to have, and I'll also include these in the email when I send it out with the recording tomorrow. And then I will put these on the website once we're able to do that as well after the government shutdown is lifted. But we're going to start with the GPM one right here. As you can see here, the GPM mission, we go way back. This was launched on the 27th of February, 2014. And it's a global precipitation measurement mission. And as you may remember that one of our former campaign team members, Dorian Janney, who has since retired from as a NASA contractor, she was on the GPM team as one of the lead educators on it as well. But she was on our campaign team for, I'm going to say, the first 4 or 5 years, actually maybe 6 years of the campaign. So, but she retired actually 6 years, probably into year 7. So yeah, so most of the campaign so far. But she was on the campaign team, but she did a lot with GPM. So here we go.
Through rain and snow, hurricane, typhoon, and monsoon, flash flood and bomb cyclone, for 10 years, the joint NASA-JAXA Global Precipitation Measurement Mission has measured a lot of water. GPM's core observatory satellite launched from Tanegashima Space Center in Japan in early 2014, becoming the first satellite to be able to see through the clouds and measure liquid and frozen precipitation from the equator to polar regions using a radar.
GPM will give us a much better picture of rain and snow falling across our planet. Knowing when, where, and how much it rains or snows will improve our understanding of Earth's weather and climate cycles.
Now, in its 10th year of operation, we look at 10 events brought to light by this groundbreaking mission. In its first year, the GPM Core Observatory satellite caught the heavy rains of the Indian monsoon. The monsoon is a seasonal wind and rain pattern that can account for up to 60% of the region's yearly rainfall. GPM allowed us to see precipitating systems like monsoons as a whole over both land and ocean. These satellite data allow researchers to study the variability of the monsoon, as well as how they impact agriculture, flooding, and landslides in the region. In 2015, Tropical Cyclone Kilo slowly meandered across the Pacific Ocean for 21 days. Because of its long lifespan, Kilo created a kind of open ocean laboratory for the mission to study the development of the tropical cyclone in a way only possible with a global satellite. Kilo was so long-running that GPM caught it 6 times, and as both a hurricane and a typhoon after it crossed the international dateline. In September 2016, Matthew became the first Category 5 hurricane in almost 10 years. It strengthened from a Category 1 to a 5 in less than 24 hours, leaving a wake of destruction in its path. As Matthew traveled through the Caribbean, Data from GPM and a suite of other satellites allowed researchers to create a multidimensional picture of the hurricane in order to study the complex atmospheric interactions. Less than a year later, Hurricane Harvey became a Category 4 as it made landfall in Texas. Soon after, Harvey quickly lost speed and slowly inched up the coast, resulting in a record-breaking amount of rainfall, topping 4 feet in some areas. GPM was able to track Harvey and the ensuing flooding because of its product called iMerge, the Integrated Multi-Satellite Retrievals for GPM. iMerge combines information from whatever group of satellites is operating in Earth orbit at a given time and estimates precipitation over the entire globe. This way, no matter where the GPM core satellite is, NASA can track the impact of precipitation systems and provide half-hourly data to local and regional agencies. It isn't just for rain. In fact, GPM became the first NASA satellite to measure the full range of light and heavy rain and falling snow. In January 2018, GPM observed a rapidly intensifying, or bomb, cyclone, which is marked by an extreme drop in central pressure of the system. The radiometer and radar instruments on the GPM Core Observatory allow it to see inside the storm and observe the frozen precipitation high atop the clouds. It can measure, layer by layer, the size and distribution of snow particles, which can help improve the numerical weather forecasts of snowfall. A Category 5, Hurricane Dorian became the most intense tropical cyclone to hit the Bahamas. As it churned northward toward Florida, GPM observed an important event in hurricane evolution, an eye wall replacement cycle. Here, the initial compact, more intense eye wall is replaced by a broader eye wall, robbing the inner eye wall of moisture and angular momentum, resulting in a weakened storm. Predicting eye wall replacement cycles is difficult for forecast models, and detailed data from GPM can improve the accuracy of those forecasts in time. Hurricane Laura was the strongest hurricane to make landfall in Louisiana in over 50 years. To study it closely, the GPM Core Observatory's instruments were able to quantify and compare the distribution of precipitation drop sizes. It sounds like too fine a detail, but drop size distribution can tell researchers how droplets are colliding and coalescing within the storm before, during, and after landfall. This close look at the microphysical environment can help improve numerical weather forecasts and complex climate models. GPM can show more than single storms. It can cover precipitation over years, showing us longer-term phenomena like El Niño and La Niña. These large-scale climate patterns in the Pacific Ocean can affect weather worldwide.
We need the long-term record in order to know how what's happening now is comparing to the averages and previous extremes. Basically, what's the climate? These data are really important for telling us whether we should expect variations such as we're seeing or whether perhaps they're new extremes.
A big part of the GPM story is seeing the extremes, both near and far. Early 2022 brought Australia's worst recorded flooding disasters. With iMerge, GPM was able to track and measure the heavy and persistent rainfall from a series of storms that battered the northwest and east of Australia. Providing half-hourly rainfall estimates for agencies and resource managers around the globe has revolutionized the tools to help with floods, droughts, agriculture, and disease outbreaks. For 5 weeks, GPM tracked Tropical Cyclone Freddie, the longest-lived tropical cyclone on record ever. Freddie began over the waters between Indonesia and Australia and slowly progressed toward eastern Africa, causing flooding and destruction in Madagascar and Mozambique. Over the course of the storm's history, iMerge revealed a variety of rainfall features and trends that relate closely to the variations in Freddie's intensity. For instance, being able to analyze the surface rainfall intensity and where it occurs relative to the storm's center is valuable for studying the evolution of tropical cyclones. When it comes to climate, what is normal? That's kind of a big question. But providing the best picture of what's actually happening is climatology. And GPM has made big strides in defining the annual cycle of precipitation climatology. GPM isn't alone. It stands on the shoulders of its predecessor, TRMM, the Tropical Rainfall Measuring Mission. With TRMM's launch in 1997, developing a fine-scale global precipitation record began in earnest. And while TRMM lasted until 2015, it built the foundation of that long record. Today, GPM not only has added another decade of data, but reanalyzed TRMM's data with modern algorithms. This long and growing record gives climate researchers a good estimate of what their models and results should reveal in the current era. As we continue to see climate change impact our seasons, our regions and towns, and our livelihoods, we want to know how rain and snowfall will change, where extreme weather will occur, and how often. The data from GPM continues to help researchers build on a long record of past precipitation in order to set the stage for understanding the future.
So when you talk about resilience and uncertainty, I mean, that's what you saw in a lot of this imagery coming from, this video, what GPM's looking at when it's looking at tracking these hurricanes, seeing the changes, in the land cover, as a result, from a lot of these, these storms coming in. So, that was a little brief foray into the GPM mission. So we're going to go a little further in. Once that rain hits the ground, where does it go? It goes into the soil, right? So then we have, have SMAP. And then SMAP takes over. It looks at that soil underneath your feet. SMAP's able to get a global map of soil moisture every 3 days with an active radar, passive radiometer. Well, the active radar, on SMAP hasn't, worked for a while. The passive radiometer is working, but we're actually using data off the European Sentinel-1 satellite for the European Space Agency. So we're getting amazing data from SMAP still. So, you see here, it launched the 31st of January 2015. So you're gonna see someone familiar in this video. You're gonna see Dr. Erica Podest. She was, as you know, she's working on the NISAR mission now, but she was a vital part as a SMAP scientist with this mission. We worked with her pretty closely on SMAP. I was the education lead for SMAP for several years. And some of you may remember for 1 year, we had the Globe, the SMAP soil moisture measurement campaign for 1 year, which was really cool to have that for 1 year. And you may have taken observation measurements with the SMAP block pattern soil moisture protocol. That protocol I co-wrote with Dr. Dixon Butler. So we co-wrote that back in 2014 in preparation for the launch of the SMAP satellite in January 2015. So that was to, we always had the gravimetric soil moisture protocol. We wanted to write one that aligns to how SMAP measurement measures the soil moisture, and that's volumetrically. So we wanted to do that so we can do some comparisons between what the volumetric soil moisture you get on the ground versus what SMAP gets from space. So here's a little bit about the SMAP mission.
Our future is all about water. Too wet where you want it dry, too dry where you want it wet, and you need water for plants to grow. SMAP will help address this issue by tracking water around our data.
SMAP is a acronym for Soil Moisture Active Passive. It's a satellite that studies the Earth's moisture content, where it is, where it comes from, where it goes.
Soil moisture plays a very active and vital role in the water cycle, and we all depend on it in ways that we don't realize every day.
Every 3 days, we'll have a soil moisture map of the entire Earth. And it will allow scientists to track water availability around the globe, which will also help in guiding policy decisions.
We can use the data to help forecast crop productivity, conditions for floods to occur, the extent of droughts, risk for wildfires, and also for vector-borne diseases that can occur in regions where there's lots of surface water.
And it'll help us mitigate the impacts that these phenomena have on people's lives. Soils are like sponges, they can hold a certain amount of water. And if we know the amount of water in the soils and we know that there's a big rainstorm coming, for example, and that the soils are near saturation, then we can predict that that area might be at risk for flooding.
When there's a lot of moisture available in the soil, it can support stronger thunderstorms. So being able to understand the soil moisture state is also useful for weather forecasting in the near term.
We're going to launch on a Delta II launch vehicle, goes into a polar orbit around the Earth. And we deploy a giant dish. It's a 6-meter reflector, so it unstows like a camp chair would.
What the big spinning antenna allows us to do is to make the measurements over a very wide swath, 1,000 kilometers, and that's the secret to our being able to make our measurements every 2 or 3 days.
This is the first time that such a large deployable mesh antenna is being used for microwave remote sensing application.
We don't ever do the same thing twice. And SMAP follows along that same formula.
It's vital to help us understand what our planet's doing, as well as to support these applications that'll touch everybody on the planet in a fairly significant way.
The measurements are really important. In terms of our future, one of the biggest issues is water, and SMAP will help us better understand this mobility of water from one place to another. I think it has the potential to touch everyone's life.
All right. Now we're going to go into one that's near and dear to the campaign and, of course, me, because I'm on the ICESat-2 team. Ice Cloud Land Elevation Satellite launched 15th of September 2018. And now we're getting to specifically a satellite that actually measures the height of trees from space. And of course, you know that this isn't all it does, because its primary objective is looking at the changing elevation of sea ice and ice sheets across the planet. But because it has a laser altimeter on board, it measures anything that has height or elevation. So everything from any type of landform to bodies of water, even the oceans. So, but since trees have height, ICESat-2 has measured over, several 100 billion trees so far. So here we go. And, I apologize, but this is like the best video that we have for ICESat-2. It's my favorite one. So we've shown this multiple times, probably at least once a year in the campaign, but this is the, like the best one that explains the most about ICESat-2 and why it's so important.
From satellite data, we have a very good handle of how our Earth looks like. We can see oceans, we can see the sea ice, we can see our forest. What is much, much harder to measure is how high things are on a global scale, almost impossible.
ICESat-2 adds the third dimension, the elevation. Repeating measurements from ICESat-2 will allow us to measure changes in the ice sheets or in the ocean or in land.
ICESat-2 is designed to measure the changes that are going on in the cryosphere, in the polar regions.
All the change is at the edges. Those are the steeply sloping parts of the glacier that interact with the ocean, and that's where all the action is. That's where all the mass is being lost.
In order to estimate the mass changes, we need to know the height of things. The mission ICESat-2 carries a single instrument. It's called ATLAS, the Advanced Topographic Laser Altimeter System.
ATLAS sends out small pulses of laser light 10,000 times a second. And by measuring precisely how long it takes that light to go from the spacecraft down to the Earth and back up to the spacecraft, allows us to figure out what the height of the surface is beneath ICESat-2.
We need to measure the time of flight of a single photon or a single laser pulse with a precision of a billionth of a second.
NASA engineers had to come up with entirely new ways of measuring time very precisely.
A billionth of a second translates to an elevation change precision of just a few centimeters. Climate change is amplified in the polar regions. ICESat-2 is designed to measure those areas and will help us to understand what's going on with our planet.
One thing I always like about that video is when you hear about that, when he says about the billionth of a second number is how it translates to a few centimeters. What he's really talking about there is, ICESat-2, the instrument on board is called ATLAS, as he mentioned, the Advanced Topographic Laser Altimeter System. That's the altimeter on board that's firing the lasers that you see here in this little cartoon of ICESat-2 with the green coming out of it. But, that translation means that, ICESat-2 can measure changes. ICESat-2 has a repeat orbit every 91 days. So it hits the same spot on the Earth every 91 days. So, let's say it takes an observation one day, 91 days later, it hits the same exact spot. The ATLAS instrument is able to detect changes as small as 2 centimeters. So if the ice melts or shrinks by 2 centimeters, if the tree, the tree height grows, or let's say it loses leaves and the height decreases because it lost some leaves by 2 centimeters, it's able to detect that. That's just, still mind blowing to me, that it's able to detect something that precise, that small. So that's, one of the reasons why. So, what I'm showing you here with these satellites is, this is how we measure these, this uncertainty on a global level. Yes, we're looking at specific areas on the Earth all the time because we're moving around the planet, 15,000 miles an hour with these satellites. We're looking at, the uncertain changes, and what we're trying to document these changes and understand them better, right? So, and I'll pass it over to Peter in a couple minutes to, understand, here we have these global level changes, how do we bring it down to that local level? But before that, I want to go through a couple more of these satellites. So here we have, since we're still talking about trees, we have GEDI, the Global Ecosystem Dynamics Investigation. You've all heard about this. If you've been part of the campaign for any, a couple webinars or a couple years, whatever. This is an instrument on the International Space Station, and this was launched, not too long after ICESat-2 was launched into space. This was launched on the 5th of December of 2018.
So we often talk about the biomass of the forest. All that is how much do the trees weigh? If you know their biomass, how much they weigh, half of the biomass of a tree is carbon. My name is Ralph Dabaya. I'm the principal investigator of the GEDI mission, and I'm a professor of geographical sciences at the University of Maryland. It's really critical that we understand what the current carbon content of forests is today. We need a good global map of where the carbon is. The reason we need that is because whenever we cut down trees, we're going to release carbon into the atmosphere, and we don't know how much carbon we're releasing. GEDI will tell us how tall the trees are. By knowing how tall they are, we will know how much they weigh. By knowing how much they weigh, we will know how much carbon is being lost into the atmosphere.
So GEDI weighs about 1,000 pounds and looks about like a refrigerator. So it has a telescope that's about 80 centimeters in diameter, has 3 laser ports, and shoots out 4 laser beams that are then dithered really quickly in between shots. So it makes 1 laser look like 2. So I'm the instrument scientist for GEDI, and that's sort of the translator between the engineering and the science. So Ralph and I, we've been working on GEDI for over 20 years and trying to get the technology ready and the science ready, and so we could fly a mission like this. And, it's been great to get to this point. Okay, so GEDI is a laser altimeter. So it's an active optical instrument. So we have lasers that emit pulses of light. They travel down to the earth, they get reflected from the earth, and then we receive the reflection. So we time how long it takes to get there, which allows us to measure the range to the surface. When the pulse of light hits the surface, it gets distorted and stretched out by any structure that's there.
It looks almost like an echocardiogram. It's a distorted Gaussian waveform, technically speaking. And where the amplitude of that waveform is bigger is where there's more canopy stuff. There's more leaves and branches at a particular height. And where the amplitude is smaller, there's less canopy material.
The overall goal of GEDI is to systematically and consistently sample the vertical structure of the world's forest. So we can estimate from that structure the carbon content of the forest.
Really, one of the coolest things about GEDI is that we're going to get upwards of 10 billion estimates at how tall trees are. It's highly likely that trees on your block are going to be measured by GEDI, and you'll be able to see how tall they are. We simply do not know how tall trees are globally. So this is really, really exciting and really cool. You can take your kids down the block and say, hey, GEDI measured that tree.
So as you can imagine, a combination of the tree height measurements from the GEDI instrument on ISS with the tree height measurements from ICESat-2 and the globe tree height measurements, you can see that we have such a great, robust database from the space-based observations and the ground-based observations. So yeah, so that's why we're so excited that tree height is such a major player with the GLOBE program and at NASA. All right, just a couple more to go here. Okay, Landsat, and I'm just this is I just have Landsat 9 up here as an example because, as you know, there are 9 Landsat missions. Then there's a Landsat Next, which is one of those the next one that's kind of on hold, which Peter has talked about before. But I have Landsat 9 on here, launched 27th of September 2021. But the video I'm going to show you is going to be the Landsat 9 things.
Landsat archives its 9 millionth scene. Each scene is a satellite image from space, about 115 miles wide. Researchers and, well, just about anyone can download scenes from the Landsat archive managed by USGS. Landsat holds the title for the longest continuous space-based record of Earth in existence. That's 50 years of scenes like these, helping scientists and researchers understand how our planet is changing over time. It will take Landsat 9 and its sister satellite, Landsat 8 days to image all of Earth's land and coastal areas. That means we get a complete picture of Earth every 8 days. In this case, 2 satellites are better than 1. Landsats 8 and 9 can work together to provide near real-time data about what's happening on the surface of our planet. Landsat collects images of each of our planet's 7 continents. Farms, forests, waterways, glaciers, urban areas. Landsat sees it all. Remember, you can't manage what you can't measure, whether it's deforestation in the Amazon, or ice loss in Antarctica, or urban sprawl in Shanghai.
Liftoff. Time 17:56. We have liftoff.
Landsat 6 launched on October 5th, 1983.
You kick motor right now and take Landsat to its final circular orbit.
But it never made it to orbit. NASA's team of scientists and engineers got to work immediately to figure out what went wrong. Turns out it was a rupture in the rocket fuel chamber. They used failure as an opportunity to learn. 6 years later, the team launched Landsat-7,
Liftoff of the Delta-2 rocket with the advanced.
one of the most technologically advanced Earth-observing satellites of its generation, still in use today. At least one Landsat satellite has been orbiting Earth since 1972. That's nearly 50 years of steadfast observation. That first Landsat proved we could gather digitally encoded data from space and changed the way we look at Earth forever. Never before seen snapshots of land resources and the environment would be key for critical decision-making decades into the future. Landsat collects light. How intense that light is tells us about what's on the ground. You can think of intensity like shades of a different color. Landsat 9, the newest satellite to join the Landsat fleet, sees 16,384 shades. That's 4 times the depth of color of the previous Landsat, meaning we'll be able to see more detail in darker spots like coastal waters and dense forests. True color images are made by combining red, blue, and green light. Combined together, these visible bands of light make up all the colors in the rainbow, and all of Landsat's true color images. Landsat also captures light that we can't see. That type of light can reveal some incredible things when you look at a false color image, like the difference between types of plants, how healthy those plants are, healthy coral reefs, and even dead coral reefs, fire tracking, ocean pollution. The possibilities are nearly endless. There are 2 instruments aboard Landsat 9. OLI-2 is all about light. Once in orbit, OLI-2 collects sunlight reflected off Earth's surface. The light passes through a set of filters to separate out 9 specific wavelength bands in visible and infrared frequencies. Each band provides different pieces of information about what is down on the surface. The second instrument aboard Landsat 9, called TIRS-2, collects thermal infrared wavelengths, or temperature signatures emitted by the Earth itself. "50 years ago, the U.S. Geological Survey had an idea. Satellites orbiting Earth that could help us monitor our natural resources. Today, the Landsat program is jointly managed by NASA and the USGS, providing an unparalleled record of Earth's changing landscapes for the benefit of all. 50 years of satellites. 50 years of life-changing data. One legacy continued with Landsat 9.
All right, as you can see, a lot going on since 1972 with Landsat and looking at that change over time. All right, so now to our 2 newest missions here. Well, I should say the newest mission, Earth observing mission, NISAR. And then we're going to finish off with GRACE, even though GRACE has been around for a little while. The picture that I'll have up here is GRACE-C. But this is a short video on NISAR. I kept it short, the shorter video, because we learned a lot about GRACE with Dr. Erica Poda's talk on last month's webinar. But here we go.
NISAR is a collaboration between NASA and the Indian Space Research Organization. NISAR is a radar satellite mission to measure earthquakes and volcanoes, ice sheets and sea ice, and forests, ecosystems, and any other thing that's changing at the scale of a centimeter on the Earth.
We are working together, and it's a great mission it is going to be with 2 different kinds of radar images that it is going to take. and give a lot of science data for all the science community who are going to look at Earth in a different perspective.
We can effectively make three-dimensional movies of the deformation or the movement of the Earth down to millimeter or centimeter scales.
NISAR is being built as two parts. The payload is being built at JPL, and the second part will be a spacecraft, which is getting right now realized at ISRO. NISAR is going to get launched from our launch pad at Sriharikota. The entire world's excited to see what comes out of NISAR.
NASA's Earth System Observatory consists of a series of Earth-focused missions that will work together and complement each other to produce a holistic 3D view of the Earth. NISAR is going to be the trailblazer for this observatory. We're going to learn more about processes related to climate change and assist decision makers and planners to mitigate natural hazards and manage natural resources.
These data will make a major difference in understanding the Earth and helping future generations live sustainable lives.
NISAR is a mix of the two cultures, and it's nice to see that we are almost the same. I'm sure the outcome is going to be something beautiful. We have taken the best of both the worlds and tried to put in NISAR because we see something very beautiful getting realized every day.
All right, as you know, NISAR has been launched, but let's finish up before I pass it over to Peter with the GRACE mission. All right. So as I mentioned, all those missions that are part of the campaign, those are the things that we're using to, look at that uncertainty on our planet, globally. So how do we, I'm going to pass over to Peder Nelson now because, as you know, Peder is, an expert of, looking at that data, looking at that comparison data between the space-based and the ground-based data and how to bring that down to a local level. So without further ado, I'm going to go ahead and stop sharing. And Peter, I'm going to pass it over to you. So go ahead and take it away.
Thanks, Brian. I appreciate that. And let's make sure that I can actually do this. New computer and everything. So I'm going to share my sound because one of the things that I want to highlight is really how important our ground observations really are. And one of the things that I want to highlight is that it's important not only to make those measurements, but to actually share them and to archive them so that they can actually be able to be used by future students or by future researchers and anybody who's sort of interested in what is happening on Earth, right? So that to me is one of these things that I want to highlight as an ongoing challenge, actually, is where do we store our ground observations, especially if we think about tree growth? How long does it take for that tree to actually go through its full life cycle? And that life cycle actually includes that decomposition process of the carbon cycle, right? It's not just about that tree growing tall and always being green and having leaves and doing photosynthesis and doing that part. That's what we like to focus on because that's the obvious thing. And, you know, but I want to share with you all a place where I'm sharing some videos that highlight what we're actually seeing on the ground. And I think this is an important part that you know, we can all take on and really add to the still photos, that sample of sunlight that we're getting with Globe Observer land cover or clouds or tree height. All of those things are doing exactly what that satellite, the satellites up in space are doing. And here, Land Trender is actually an algorithm that scientists are using and communities are using to look at change over time. And I highlight this because this has been going on for 25 years, actually, and was part of what brought me to the Globe community. It's in search of data on the ground that we can use to combine together with that satellite data. And what I mean by that is we're seeing in the Globe database ground photos of things like this top banner image, right? And I want to highlight how there is actually, you know, a lot of information here that tells me about how quickly things are growing back, like these trees here at the top. You know, trees only grow so fast. And so if they are below 50 feet or below a certain height, we might be able to use that as a way of inferring something about the age or time since past disturbances. And then, you know, here you actually see some shrubs that are growing up. And that also indicates something about that ecosystem and about how long have things been growing in this space. Green usually indicates photosynthesis, right? And so that's some indicators that we're using. But you might also see brown leaves that are out there. Those brown leaves are things that we are recording and might, again, give us indications about precipitation, about differences in who is in this area, right? And then I want to highlight something that is incredibly important that we're capturing in our photos, in our light samples, that we are not recording in any database. So this metric is actually not available, but all the scientists want to know how much standing dead trees are there. And I mean that, you know, because that's part of our carbon cycle and actually something that the laser scans might be recording because they don't know whether they're getting green leaves or needles or whether they are bouncing off the ground. Those are some of the details that we have to infer sometimes or go back to the numbers. And if we have even these photos that show, wow, there's still a lot of standing dead trees that might be part of that sunlight reflectance that we're measuring. So I want to point to you all, upcoming GIS Day 2025 is, I think, November 15th. And this is a yearly activity where we look at how we actually move from the physical world, like where we're seeing these trees, where we're making our globe measurements, and how we actually start working with digital data to make some understanding of that in the geographic information system place of things. I have put together a little bit of a video here, and I'd like to share with you what an area looks like after a wildfire. And I want to highlight this, in particular, because if we go to looking at all of this, here is actually where water comes straight out of the ground. You're actually looking at a water spring here. And what and this may not be what you think of as where water comes out of the ground, but this is one of those really important pieces that we want to be able to see, right? So hopefully you'll be able to see this, but I'm getting a note that Zoom doesn't like what I just did. So I am going to click play right here. And here, what you're starting to see is actually the process after a wildfire. You are starting to see the way that flame, fire changed the landscape. Sometimes it left bare ground. Sometimes those trees that were left standing start falling down. Sometimes people are the ones that are responsible for that, which we can see right here, some evidence of tree cutting, actually, compared to some other stumps or other areas that might actually have fallen over more naturally. So there's indications here that we can start using to understand how people responded to this particular landscape event. A lot of times you'll see after a wildfire, we get grasses, those annual vegetation that come back and grow really quickly so that they can use that bare soil as an advantage. This is what we're actually seeing when we're making our spectral measurement, the sunlight reflectance measurement. We're actually seeing a lot of black on the landscape because of that charcoal and the way that the carbon cycle and the intensity of the flames. Actually, we get some indications of the bark sometimes. In this case, we can see that the fire was so intense that it got all the way down and into the heart of these trees. As we look around, you can actually start to see something that you may not appreciate how it started. This coarse woody debris is one of these things that we see in natural water systems. The amount of trees and vegetation that go in is one of those things that slows water down, that actually ends up creating maybe flooding events down the line. But if you notice, the size of trees like this are one of these things that really affect the way that water moves through the landscape. So it may be a subtle thing, recognizing that we have trees laying across this area where we have water flowing, but imagine this landscape in 50 years. These really large trees like this, at least in this landscape, will still be here. These trees that we're looking at are almost 6 feet in diameter. That's almost 2 meters across. And when you go to a different landscape, you can see actually here is what shrubs look like, a whole different land cover type. And one of the things that I'm pointing out here is shrubs, at least here, are burrow sprouters. They come up from below. And so when we see shrubs on the landscape, they might actually be relatively young, at least the part that's green and photosynthesizing. But you can see that sometimes the skeletons, what's left behind afterwards, has taken a long time to grow because shrubs, in this case, may not grow as fast as trees, and or they grow in a different way. And as we look around at how much a bare soil is there, that is something that we really want to pay attention to, because again, this might be what we're seeing, and whether it's dry soil or wet soil is one of those important pieces that the satellites are measuring. And so as we look around at landscapes and how they actually look on the ground, just recognize that our satellite measurement is very similar to what we're seeing here. And it's made up of all of these different components of land cover. And they're not stable. We're going to have shrubs growing over time. We're going to have these trees continuing to stand there and be wildlife habitat, but they will also go through changes. Importantly, you see in this video a very subtle thing about how sunlight reflects differently into the camera, actually. And so these are all really important parts of what we are actually seeing in our landscapes. And I want to end here with a little video of me in a place and something that we really want to warn you about and warn all of us about. Places that have undergone changes like this, land cover changes through a disturbance event, especially wildfires, but many different events like this. When wind comes through, it becomes a really dangerous place. And so hopefully you will find postings of signage or other things that might warn you. But recognize that this is one of these things that makes our world really challenging to really describe our environment. How safe is that place? It may actually be different on one day to another, depending on features like weather or like wind. And again, this is that post-event landscape that we're trying to track. And so just because a big event like a hurricane or a fire or people plant trees, just because those things happen, there's still a story that will be unfolding in the future. And so never think about your place as boring, because there are these different things that are happening that we're recording with Globe Observer. You know, those surface conditions really help us to identify how, what might happen in an area. It allows us to really, keep track of this change over time, this cause and effect. And I'm going to end here with this video that is available on My NASA Data that we have highlighted and was created before we came to the Globe program, because we really need this on the ground information. And that's where we ran into a lot of problems. And so we think about uncertainty out there. Scientists are looking for this information that communities have. It might be in our Globe database, but it might also be in other places. And so as you think about this next year, remember that our data that you're collecting in the Globe database needs to also become resilient to changes. And those changes could be the way that scientists are working with their data, but it could also be how we share this information with each other. So, we really appreciate you taking this moment to think about resiliency, longevity, and how these science principles actually come back to the world that we're living in. And recognizing that the world that seems static is actually undergoing these changes. And that's why we need to keep these floating observatories in the sky out there collecting data when maybe we don't have the resources on the ground to actually get to these places. And I want to really stress that there's a lot of people who are doing this. This week, there is a whole group that is focused on global forest observations. This has informed everything that we're doing here. And so hopefully we will be able to see and support everybody going forward, but there is uncertainty. always, and there has been for over 50 years as we've been doing this remote sensing piece. It's never guaranteed that those satellites will stay up in space, and it's never guaranteed that we will actually see the same world as what past people have seen, or what you saw last year when you went out and made your measurements. So please go out there and continue making these tree observations, and recognize that just because there's trees not in that location today doesn't mean that in the future there will not be those trees, that trees will not encroach on your landscape. That's something that we've seen over time. And it's really an amazing thing to think about and recognize that trees are witnesses to the world as much as we are. So please share with us what you want to do, any information that you want us to share with you or highlight in our Trees Around the Globe student research campaign, because this is really a lifelong, a generational commitment to watching and being part of this carbon cycle that's out there. So thanks for being part of our kickoff campaign and videos this year. And we look forward to seeing what is happening to the state of your trees, and really what is the value of those trees and those ecosystems to your community. It's not just a value today, it's actually a value going long into the future that sometimes is gifted to us. So what is the value of all of this carbon and life that we have around us? Brian, take us out for today.
All right, thank you, Peter. That was excellent. Thank you for bringing it home for us. So excellent. So yeah, I just want to share a couple things. One thing is, you might have saw on the agenda. One thing we like to do in order to as Peter mentioned, about us keep taking these measurements. We'd love to do something, as part of the campaign, some type of intensive observation period, for tree height and land cover that, is, part of the campaign, not a grandiose all over globe thing, but something that would, bring together, our campaign members to, participate in that. And we'll talk about that, over the next couple weeks, and maybe we'll talk about it more at the next webinar, before the next webinar, because that's kind of the end of November, and I'm going to share my screen again because I want to show you information about the next webinar, when it's going to be. So I'm going to show you this here. This is the last slide, but yeah, we're hoping to do something, and to do some type of intensive observation period, whether it falls, in the fall, or leads into the winter time. That's fine, but we like to do something where we have some type of concentrated, intensive observation period where we try to get a bunch of observations for tree height and land cover, over a small period of time, or a shortened period of time. But our next campaign webinar will be on Tuesday, the 25th of November, 2025. And please note the shift in time. We usually do it about 1 p.m. Eastern time, but we're going to be doing it at 2 p.m. Eastern time. And our speaker will be Adriana Northcutt, and she is coming to us from Alaska. And she was a 17-year educator in Juneau, Alaska School District. And she's now the STEM educator and regional energy catalyst at SSP from the Renewable Energy Alaska Project, also called REAP. But she's going to discuss, and you can see here in the title, the value of a tree, roots and culture, community, and the future. So she's going to discuss how a single tree holds a deep and layered value that extends far beyond its physical form, and how culturally trees are living symbols woven into indigenous knowledge systems, traditions, and stories that teach respect for the land and the interconnectedness of life. She'll also discuss how a place-based understanding reveals how specific trees are uniquely adapted to their environments, continually being shaped by the local ecosystems and communities that surround them. And then she looks at all of this through a scientific lens, and how trees are powerful actors in the carbon cycle, which is a huge focus of what she does, the carbon cycle, capturing and storing carbon dioxide through photosynthesis and helping to regulate our climate. Really focusing on how the tree's presence improves air and water quality, supporting biodiversity, and building resilience. There's the term again, resilience against environmental change. And then after that, once again, Peder will bring it home for us, because Peder is an expert at bringing it home for us. We'll highlight some recent work in Alaska that ties together space-based and ground-based land cover and tree canopy observation. So, please come back for that on the 25th of November, and please know that time change. And I will be sending out that invitation this week. I try not to send them out too close together. A reminder for one webinar with the same time a new one comes out, it gets a little confusing. I've had people complain to me about that before. They're like, "Oh, I don't know where to go to. You send out so many emails." But yeah, I'm kind of like that constant contact, type thing. So, but yeah, so please come join us for this one. And as a reminder, the recording for this webinar will be sent out. The link to the YouTube link will be sent out tomorrow morning. Once I get all that done, and also as a reminder that we can update the Globe website during the current United States government shutdown. If it would happen to reopen tomorrow, we will get it up. I will get it up on the Globe website on our webinar campaign webinar page first thing tomorrow. So, but you'll know there will be signs when you get an email saying it's up on the website. For those international folks that may not see that news, but we'll see. We don't know. We have no idea. But you will definitely get an email with the YouTube link to look at the recording. And I will also include all the links that I put in the chat to all the mission videos, as well as some of the links that Peder had in his presentation today. So I'll include those all in the email for you to take a look at as well. So I will go back from stop sharing, but also think about, Peder mentioned also about, what you'd like to see in the upcoming months for the Trees Around the Globe Student Research Campaign with Year 8. So once again, for all of us here at the Trees Around the Globe Student Research Campaign, thank you for being here. And those of you who are watching the recording, thank you for watching the recording, and sorry you couldn't be with us. And those of you who are here now and watching the recording again, thank you so much for watching again. So thanks, everyone, and take care. Bye-bye.